Hello, everyone, and welcome to Meet the Experts. I'm Katie Wolfson with the National Center for Atmospheric Research, and we are so excited to welcome you to another month of Meet the Experts. This is a monthly program where we connect students like you to experts here at the National Center for Atmospheric Research. We can't wait to hear your questions throughout the program. Please feel free to type in the chat if you need anything at all. Tim, Tiffany, and I are here to help you out and to also share any of your questions with our experts. So please feel free to ask questions throughout the program. We'll also have time at the end. Also, if you would like them, there are captioning. Closed captioning is available, so you can turn your captions on or off down below. If there's anything else you need, let us know. We are so excited to connect with students today from Colorado to Florida to California to Seattle, Washington. We have folks from all over joining us today, and we're so excited to connect with you. So without further ado, I'm going to go ahead and introduce not one, but our two experts today. So today we have Dr. Rebecca Centeno and Astrid Maute. So Astrid and Rebecca are both scientists with the High Altitude Observatory Lab, and they're going to talk to us a bit today about space weather and what that means. So before, though, we actually have a question for you students. So we have a poll question. We want to know, how does the sun impact your life? How do you think the sun impacts your life? So I'm going to throw a poll question up that should pop up in Zoom for you here. So please feel free to check as many of these as you think are true. So how does the sun impact your life? It doesn't. It provides energy for plants. It disrupts radio communications. It produces power outages. It helps me generate vitamin D. It makes the GPS on my phone stop working. And it gives me a sunburn. So which of these do you think are true? See some answers coming in here. We would love to hear, okay. Which of these do you think is true? How does the sun impact your life? If you have other ideas too, feel free to type those in the chat too. If you think of some other things maybe you don't see on this list of ways you think that the sun impacts you. Okay, we're gonna give it about 5 more seconds, so get your answers in. All right, let's go ahead and check out those results. Okay, the results that we can see, Astrid and Rebecca, it looks like people voted for provides energy for plants, helps me generate vitamin D, and gives me a sunburn, is what how people think the sun affects them. What do you think?
That's all true, yes. But what we will talk about today is not actually about sunburns and about biology and plant growth. We will talk about the other options. So the disruption of radio communication, how the sun can affect our power grid and even cause power outages, and how it affects GPS, so our navigation systems. And it all starts at the sun, so very, very far away. And that is what Rebecca is studying. So maybe you go ahead, Rebecca, and tell us what you are doing.
Yeah, right. Thank you, Astrid. Yes, it does start at the sun, and it starts with something that we call space weather. And space weather is a term that refers to changing conditions on the sun and how those changing conditions affect the interplanetary medium. This is throughout the entire solar system, the space in between the planets and the planets themselves. And of course, we're mostly interested about space weather and how it affects the Earth planet. So the condition can actually affect the space around Earth. And even if we don't directly notice it, the sun is changing all of the time. And these changes on the sun can come in many different forms. There's changes in the radiation. This is the light that the sun emits. There's changes in the amount of particles and material that the sun expels constantly out into space. There's changes in the magnetism on the surface of the sun. And just like weather on Earth, the sun has a weather of its own. It has for instance, it has a wind that's blowing out into space all the time. Sometimes that wind is stronger, sometimes that wind is weaker. It also has storms, and these storms can actually be rather violent. So let's talk a little bit about solar storms. Solar storms are explosive events in which the sun releases large amounts of energy and material out into space at very, very high speeds. The video that you're seeing right now on the screen is a type of solar storm called a filament eruption. The filament is that dark, sort of elongated piece of material that you see sitting above the sun's surface and that is now being kind of expelled outwards. That is just solar material, large amounts of solar material that is kind of trapped and confined by magnetic forces that hold it and pin it down to the surface. But when these magnetic forces break, they release all of this material all of a sudden into space. Now, a big solar storm can eject up to 1 billion tons of solar material out into space in one single event. And this is equivalent to the mass of about 500 million cars. So it's really large volumes of mass from the sun that get ejected out into space in each event, in each solar storm. And this material can travel at really high speeds, up to millions of miles per hour. So when these storms are aimed in the direction towards Earth, we can see the effects on the Earth hours to days later. And if Katie is kind enough to bring up the image of the aurora, this is one of maybe the most common effects of solar activity and solar storms on the Earth's atmosphere. It's beautiful displays of lights in the nighttime sky. It typically happens in places at high latitudes of the Earth. And they're also called northern or southern lights. But this is not something that I'm going to talk about. I'm going to actually pass it on to Astrid, because this is more in the field of what Astrid does, such as the impact on the Earth's atmosphere of space weather. So Astrid, can you tell us a little bit more about what you do?
Sure. Thanks, Rebecca. Yeah, as Rebecca said, I study the effect of these solar storms on the Earth's upper atmosphere. And here Katie brought up the different layers of our atmosphere. So we are down in the troposphere. And then the upper atmosphere kind of starts around 900 kilometers. That's around 60 miles. And you saw the picture of the aurora from Rebecca. So the bottom of the aurora is around 100 kilometers, sometimes a little bit lower, depending on the kind of aurora. And it's the upper atmosphere. We have satellites, rockets, and so on in that region. What you can see here is that the storms, they generate the aurora, and the storms have different sizes. So, and we measure this as energy. And to give you some ideas, very powerful storms, we call them superstorms. They can bring around 5,000 gigawatt energy into Earth's upper atmosphere. So for comparison, the US energy consumption is around 3,300. So that's more than the whole US consumes. And a watt is energy per second. So it's a rate. And Katie showed here the aurora, and you can see that the energy goes mainly in this circle here. So why are we interested in something which happens hundreds of kilometers above us? And you might know that we have a lot of technology up in space. So Katie, if you could bring up the figure with the impact. Yeah, thank you. So this is from NOAA, a schematic about the space weather impacts. So one thing we have in space are humans. We have people on the International Space Station, and we want to protect them if a solar storm comes our way, so that they go into their secure room. We also have satellites up in space. And not only a few, we actually have a lot of them. So we have a figure here. Katie, if you could bring up the figure with, yeah, thank you. So all these dots is something in space. And the blue dots are satellites. The red dots are rocky bodies, and the gray is debris, so garbage, junk we just left in space. And what we want to avoid is that satellites we actually use collide with a rock or with another satellite or with the debris. So people are working on forecasting the conditions in space to avoid these collisions. And we have this picture here, Katie is showing, where actually two satellites collided. One was not in use anymore, but the other one, they collided and generated thousands of pieces, which then can harm other satellites. So every point here is one piece of debris, even years after the collision. So the collision was 2009. So it takes some time for all the debris to come down into Earth's atmosphere. Another effect of space weather is what we use quite often is the global navigation satellite system. You might know the GPS system. There's Galileo and so on, different satellites. And it relies on that we have a good connection from the ground to the satellite and back. So for that, we need to know what are the conditions in the upper atmosphere. So if a storm is coming, we might lose the connection, or we don't really know what the conditions are, the path of the signal going to the satellite and back. So this, for example, GPS is also affected by Earth weather. So this is also something we are studying here at NCAR. And what is cool is we have scientists who really study Earth weather and Earth's climate up to the sun. So we have the whole chain of connection here. And what is shown here is a few things which also generate space weather. One is earthquakes, like this energy released within a few milliseconds and generating waves. And these waves propagate up into the upper atmosphere and can, as indicated here, disrupt our signal, our connection to the satellites. We can have volcanic eruption. We can have tsunamis and see their signal up in the upper atmosphere. But it's also thunderstorms and weather in the tropics, which we can see regularly up in the upper atmosphere. So this happens more regular, but the storms from the sun are huge effects compared to these. So on Earth, we can measure the conditions of our atmosphere from the ground or from satellites. But Rebecca, how do you measure solar storms on the sun?
Oh, okay, that is a really good question, Astrid. Let me go a little bit further back and start with, big solar storms always originate in places on the sun that have high concentrations of very strong magnetic forces. These are like the forces that make magnets stick to your refrigerator, but a lot stronger. It's actually the same forces. This movie that Katie is showing right now shows these are actual observations of the sun taken from a satellite in space. And you can see the sun rotating, spinning on its axis. So what you see there is the surface of the sun, and it's kind of mottled with like these black spots everywhere. We call those sunspots. And sunspots are actually correspond to high concentrations of very strong magnetic forces. This is the places where solar storms originate. And sunspots are actually dark because of the magnetic forces inside them. The magnetic forces are so strong that they actually keep the sunspots really cold compared to the surroundings, and that's why they look darker than the surroundings. But anyway, magnetism is important because it allows the sun the capability to store energy really slowly, but then release it really quickly. And that's why solar storms are often explosions, essentially. Being able to predict solar storms is, of course, important for forecasting space weather at the Earth. We ideally want to be able to predict the solar storm is going to happen, when and where. We want to be able to know whether or not it will travel towards the Earth, and what are the potential impacts that this storm might have on the Earth's atmosphere. And this actually depends on the type of storm and the physical conditions in the storm on the sun itself. If we know all of this, we can actually prepare in advance of the space weather event happening. We can take preventive measures, such as shutting down instruments on satellites, for instance, to prevent malfunctioning, or putting in place some mitigating measures that protect the power grid on the ground that we all rely on for electricity. But in order to predict anything, we first need to measure the conditions on the sun. And this was actually Astrid's question. How do we measure that? Well, we cannot go to the sun and put a thermometer in it to measure the temperature, or put a magnetometer to measure the magnetism on the sun. We don't have the technology to do that. The sun is too far away, it's too hot, it's too dangerous. We cannot do that. But we can actually obtain a lot of information about the physical conditions on the sun just by observing the light that the sun emits. So encoded in the spectrum of the light, this is all the different colors of the light, all the different wavelengths of the light, there is a lot of information about the physical conditions in the sun's atmosphere. This is the temperature, the pressure, the density, the magnetism. We can actually learn about all of those things by analyzing the light that the sun emits. This picture that you're seeing here is actually a composite image where we show the sun observed these observations in different types of light and different colors of light. And you can see it looks very different depending on which color of light you're looking at the sun in, which gives you at least a sense of that you can get different information by observing the sun in all those different lights. So the way we obtain this information is that we capture the light with telescopes, we analyze it with instruments, and then we interpret the observations by means of theory and computer modeling. And by gathering enough information from all the colors of light and from all these different instruments and interpreting the data, we can actually begin to put together a picture of what is happening on the sun. So for instance, we can actually learn about how the magnetism is distributed all over the sun's surface, how it's changing with time, and whether or not it will lead to the next big solar storm. So this actually brings me back to Astrid. Solar storms actually happen regularly. They happen all the time. How is it that we're not continuously losing satellites and losing power to these solar storms? What is it that protects us from them?
Yeah, that is a good question, Rebecca. And Katie, if you could bring up the movie. Yes. So here you see the sun, and these spots are the sun spots where the energy is. And now there is this sudden eruption, and this cloud of material with a magnetic field embedded in it travels through space toward Earth. And you see the lines around Earth. That's Earth's magnetic field in the solar wind. It's this teardrop shape. So it deflects the energy from the Earth, but eventually from the back, it goes into Earth's upper atmosphere in the high latitude region, forming the aurora, what we've seen before. So Earth's magnetic field is very important for us to shield us from the effects of solar storms. So you need a big solar storm to see effects. And the Earth's magnetic field, to give you some idea, it's around 20 to 60,000 nanotesla strong. So Tesla is a unit to measure the magnetic field strength. What is coming from the sun has a magnetic field in this cloud, but in general, it's like 1,000 times weaker, so 10 to 20 nanotesla, maybe a little bit bigger for really strong storms. So that's why Earth's magnetic field can shield us from the effect. But still, energy is coming into Earth's upper atmosphere. And Katie, if you can show the schematic of the extent of the aurora, the picture. Exactly. Thanks a lot, Katie. So here you can see two things. One is Earth's magnetic field is not aligned with our rotation axis. So this means that the north pole of our magnetic field is not at the same location as the geographic North Pole. It's actually tilted toward Canada and the US. And this means we are more exposed to the effects of solar storms in North America than, for example, in Europe. So these circles are tilted towards North America. And then the color shows if you have a weak storm, it's kind of the bluish color. So the aurora or most of the energy goes into above Canada. But if you have a very strong storm, so the red circle, then it extends to the middle of the US. So for example, we are in Colorado, we would see an aurora here. So it depends on the strength of the storm if you see an aurora. But the energy is not staying where it enters the upper atmosphere. It gets distributed globally. And one effect, since we talked a lot about magnetism and measuring the magnetic field, is that we always have electric current flowing in the upper atmosphere because we have ions and electrons and we have neutrals there in the magnetic field. This can generate a current, and associated with this current, as you might know, is a magnetic field. And we can measure these at the ground even. So we have a figure from a ground magnetometer station in Boulder. If you can show this, Katie. Thank you. And this is the strength of the magnetic field, or the perturbation actually. So the Earth's magnetic field is removed, so it's only a few nanotesla, measured in Boulder for a superstorm. We call it the Halloween storm because it happened on October 31st. And in the beginning, on the left, you see only small wriggles. So we call this quiet time. And then the solar storm hits Earth's atmosphere, and suddenly you see this jump to 300 up to 500 nanotesla. So very strong. And this is because the upper atmosphere is disturbed. There was a lot of energy coming from the sun, and it affected our Earth's atmosphere. So this gave you a little bit teaser about space weather and how the sun is connected to Earth's atmosphere.
Wonderful. Thank you so much, Rebecca and Astrid. I think we're going to open it up for some more questions from students. So if anything has made you curious, made you wonder today, or things you've wondered about the sun or space weather before, we would love to hear them. Or if you have any questions for Rebecca and Astrid about their jobs, feel free to type those in the chat. I do see one question here from earlier. I believe it was while we were seeing the solar storm, asking, is this what the sun actually looks like?
Yes, that's an actual observation of the sun. So it means a telescope looking at the sun and selecting a very specific color of the sun. So the sun looks differently depending on what color you select to look at. But that's an actual picture of the sun. It's a movie. Yeah.
Very cool. Okay, so feel free to throw those questions in the chat. We can't wait to hear them. I had a question for you, Rebecca, about, you mentioned telescopes to look at the sun. So what are those solar telescopes like?
All right, so they're probably not what you envision when you think of a telescope. They're very different from the telescopes that we use at home. for starters, they're actually much bigger telescopes, and they're typically enclosed in buildings. I know Katie has some pictures somewhere in her folder that she can probably pull up. Okay, so this is a solar telescope that is actually currently being built or almost finished on Haleakala in Hawaii. It's the largest solar telescope in the world. By large, I mean the way we capture the light with telescopes is by collecting the light with either a big lens, big piece of glass, or a big mirror, and then redirecting the light down the telescope. Big refers to the size of that lens or mirror collecting the light. So inside that building, there's a huge 4-meter diameter mirror that is pointed at the sun and kind of collecting the light from the sun and redirecting it to instruments that are also inside the building. We also have telescopes in space. They look rather differently. They don't have buildings around them. This one that Katie just pulled up is called Hinode. This is a Japanese, US, UK mission that launched 15 years ago. And what you can see there clearly is the solar panels. Those solar panels actually capture energy to run the instruments that are on the telescope. But the telescope is inside the golden tube that you see there. And that tube is pointed towards the sun, and the light is entering through the tube and being gathered by a series of mirrors and lenses that then send the light to the instruments behind the telescope. So that's what they look like.
Wonderful. Thank you so much. We got a few questions coming in here. I see one of our schools in Florida is asking, why did you call it the Southern Lights? Are they different from the Northern Lights?
And then there's probably the question for Astrid, but
yeah, it's a very good question. The physics behind it is the same. Energetic particles come into Earth's upper atmosphere. We have gas there, different types of gas like oxygen, nitrogen, and so on. And it excites it, so it puts the energy into the gas. And then when it goes back into the original state, it emits light once it's kind of getting rid of the energy. So that principle is the same, but there are distinct differences between northern and southern lights. One, for example, is that most times the season is different, and therefore the upper atmosphere conditions are different. The main field of the Earth is different, so this influences how deep particles can penetrate. And it's an active research area to understand all these differences between the two polar regions. So it's a very good question.
Is it essentially that southern lights happen in the southern hemisphere, northern lights in the northern hemisphere, but they actually look a little different?
I mean, they probably look the same, but it's not a mirror image. It's never really a mirror image. And you can imagine we have a bias towards the northern hemisphere. There are less observations in the southern hemisphere, so that is already difficult for scientists to really get a handle on. So we kind of project our northern hemisphere knowledge on the southern hemisphere, but now we realize maybe the southern hemisphere is different. I mean, there's more ocean, the magnetic field is different, and so on.
It sounds like there's still a lot for space weather scientists to learn more about and explore, right?
Yeah, we need future scientists.
Okay, we have another question from Ms. Birchfield's group asking, is there one main thing that you study? If so, what is it?
I didn't understand the question.
So I think is there one specialty that you each study that, because you've been kind of giving us a great overview, so is there one piece that you focus in on as a scientist?
Right, well, I study in particular how we convert the measurements of light into measurements of magnetism on the sun. And that is a field that's called polarized radiative transfer. There you go. It's a mouthful.
Yeah, I studied different aspects of what we touched on. So one is what I'm very interested in is the connection between the lower atmosphere and the upper atmosphere. So how are the waves generated in the lower atmosphere propagating up, and um, what conditions do they generate? So NASA has new missions up there, and we take the observations and try to understand better this coupling between the lower and the upper atmosphere. Um, but then I'm also on some other mission which is more focused on the magnetic field measurement. And Katie, if you want to bring up the ISI slide from the CubeSat, so these are the small satellites flying. Yeah, thank you. Um, and so these measure the magnetic field with from the current which is flowing in the upper atmosphere. So it's kind of the same concept what Rebecca talked about, where you measure the light. Only she's doing it on the sun, and this is now on Earth. And this current is flowing around 100 kilometer, and by measuring it really at 100 or close to 100 kilometer, we hope to see more the fine scale structure of the magnetic field that the current generates, and therefore better understand the current and what is causing it.
Awesome. So it sounds like you each kind of have your specialties there. So are there lots of different people studying space weather and the sun and upper atmosphere?
Yes,
Yeah,
there are. Go ahead, Astrid.
Yeah, there are a lot of different aspects. I mean, it's kind of combined under space weather, but I think it goes from the sun to the lower atmosphere, and not only the different layers and different aspects within the layers, but um, a lot is we need data scientists. I mean, working with huge amount of data now, how to analyze it, how to use it in numerical models. So that's something I do. I use models mainly. Then we need people building instruments, like how does the next generation of instrument look like to get better measurements, to better understand how, what is the condition of the atmosphere, how does the sun look like. So there are a lot of aspects, and there's also communication, very important aspect. Like if there's a space weather event coming, you need to communicate this to the people in industry who might be affected. So you can work in predicting the space weather as a forecaster, and so on. You might have to add something, Rebecca.
No, that was pretty good. I think it gives a sense of how complex. There's so many disciplines involved in this sun-earth connection, and how you make policy out of it. That it spans the gamut of possible jobs that people may have related to this.
All right, so students, there's still a lot more to learn, and there's lots of different jobs and ways that you can be involved if this is interesting to you. Let's go for some more questions from the chat. I see one of our California students asking, why is it cold in space? We have this big sun. Why is it cold in space?
Do you want to answer that question, Astrid? I think it's complicated to answer.
Yeah, I'm not sure that I can really answer it. I mean, there's not a lot of stuff in space. It's not very dense. Um, and then since it's not very dense, I mean, it depends how much energy the radiation goes through, but only a certain wavelength actually gets absorbed in the upper atmosphere. Um, so I don't know if this is the really correct answer, but I think if we wouldn't have our dense atmosphere down here at Earth, probably we would freeze as well. And then there's stuff like um, uh, transport, basically how the energy is moved around, and then reaction. So I think it's complicated. Um, overall, the energy transfer. I mean, the sun is one part, but then also energy is coming up from the lower part. But it's a good question. I
No,
should
I
check.
mean, I would say Astrid is right. I think it has to do with the fact that in space there's barely any material to absorb the light from the sun. So it is cold. This is a very it's a very technical physical question that requires sort of thermodynamical considerations to answer. But the fact is that there's basically no mass, there's no particles, is so little density that there's not enough mass to absorb the energy from the sun and heat it up.
Yeah, maybe one thing. So it's not why it's not only the mass is, I mean, the temperature. If you check out the temperature profiles in the different layers, uh, it's kind of decreasing and increasing and so on. So it has something to do with the density, but also how the energy is transferred up and down. Um, so it's, as Rebecca said, it's really several processes coming together. And I mean, the temperature is high in the upper atmosphere, but you can't feel it. So it's increasing and then kind of getting constant.
Awesome. Seems like such a simple question, right, everybody? And
Good.
it's complicated. There's a lot of processes involved. Awesome. Okay, so we have another question from California asking, will the sun eventually burn up the Earth?
I think the short answer is possibly yes. That's what we know from stellar evolution modeling. So this is the discipline that tries to understand how stars are born and sort of evolve throughout the lifetimes. The more interesting answer probably is like not anytime soon. So the sun, as any other star, was born a long time ago, and it's right now it's in its very mature phase of its life where it's really not changing that much in the big picture scale, and it will remain relatively similar to how it is now for billions of years. But eventually, in theory at least, from what we know from other stars, it will turn into something called a supergiant, where it will like expand and engulf a good part of the solar system and the planets in it. And that might actually even involve engulfing the Earth. But not in our lifetimes, for sure.
All right, go ahead and throw some more questions in the chat if you have them. I was going to ask Rebecca, you talked about solar telescopes. Why do we need solar telescopes to look at the sun? Why can't we just look up at the sky at it?
That's a very good question. No, you should never look at the sun with your own eyes. Because you'd get hurt and it can cause blindness. But that's not the only answer. We don't look at the sun with our own eyes because we actually can't see, we wouldn't be able to see very much detail on it. We need to magnify the image to start seeing the small scale details and the smaller stuff that happens on the sun that actually matters for the whole picture of how these solar storms are built up over time. I think Katie has a couple of images. Yeah, this is an image that just shows a picture of the sun taken from the ground with somebody's camera. So this is how you would see the sun if you looked at it with your own eyes, pretty much. I mean, just a bright ball in the sky and nothing else. But if you look at it through a telescope, which has the ability to magnify the image on the sun and the details on the surface, you can begin to see things like this. Now, this image was taken by a telescope that is kind of a modest-sized telescope, so relatively small, about 14 centimeters big. Again, when I'm referring to the size of that mirror or lens that captures the light from the sun. And you can see how much more detail you see of the sun's surface compared to what your eye would see. This is just an image of the sun's surface with a sunspot on it and then a little group of sunspots beginning to form on the right side. But as you increase the size of the telescope, you begin to see much more detail. So on the left, again, that image of that first telescope that was about 14 centimeters big. And then on the right, this is an image taken from a telescope that's about 1 meter wide. So much more, we call it resolved, meaning we can see more detail of the sun's surface. And this last video is actually from that very new telescope that was built very recently on Hawaii. This is a 4-meter telescope. So again, it's the biggest solar telescope in the world. And what is shown right here is just a movie of observations of the sun's surface. And you can see the amazing amount of detail. This is a tiny portion of the surface on the sun that we're seeing with this telescope, but it's magnifying the image so much that we can actually see a lot of things happening right there.
Excellent. Okay, so we had some wows in the chat at some of that. So thank you so much for sharing that with us, Rebecca. Let's go ahead. We have another question from California. Let's do this for one last question from the chat of, are there different types of suns?
Yes, the sun is a star, actually. So there's different types of stars, and the sun is just one of them. This is not my field of expertise, but the sun is actually a pretty mediocre star in many ways. It's kind of quite boring. It's not very active, despite what we've been telling you about space weather and how powerful solar storms can be. There's stars out there that are insanely active and leave the sun like down in the dust because it's nothing in comparison. The sun is a very small star, so there's stars that are much bigger than the sun. There's also stars that are smaller than the sun, and throughout the universe you can find an amazing variety of stars, and the sun is just one of them. It's just important to us, of course, because it rules our lives, but in the context of astronomy, the sun is a pretty boring star, I would say.
All right, and I think we are about all out of time today for more questions. Thank you so much, students. Rebecca and Astrid, is there any kind of final thing you want to share with the students before we say goodbye?
I just want to say that if you want to be a scientist, just pursue it. Don't let anybody tell you that math is hard. Don't let anybody tell you that physics is hard. It's if you're passionate about it, it's fascinating. It's beautiful. You can learn a lot about the universe by pursuing a career like that, and we need more scientists.
Wonderful. Well, thank you so much, Rebecca and Astrid. I learned a lot today. I hope, students, that you learned a lot too. Thank you so much for joining us today, Rebecca and Astrid.
Yeah, no worries. Thanks.
Thank you.
Yeah, thanks. I hope that everyone will join us for our next Meet the Experts on Thursday, November 11th. We are going to be talking with Gunter Legee from NCAR about ice sheet science. So that will be live on our website next week. If you would like to register for that, we would love to have you join us for there as we look a little bit closer to home as we look at sea ice and ice sheets. So thank you so much, everybody. We'll see you next time. Have a great day.
Bye.
Bye.